This conference will now be recorded.
Hello everyone. Last day we have already started the structure of sulfur dioxide and some properties also we have seen. Today we will see some more chemical properties of sulfur dioxide, that is SO2, and after that there will be another important compound of sulfur which is H2SO4, then oxoacids of sulfur and some related properties. Reducing nature of this compound. In presence of moisture, that means water molecules, it can liberate nascent hydrogen. Now nascent hydrogen means atomic hydrogen which is very reactive, and it is also possible if SO2 is present in that is it is present with some oxidizing agent, then also it can easily take an oxygen atom. So when we say that reduction reaction is going on, two things may be happening. One is that it is liberating nascent hydrogen or it is accepting oxygen atom. Okay, so both are actually showing the reducing nature. It can reduce ferric salt, that means Fe3 plus salt to Fe2 plus salt, which is ferrous. Halogens to halogen acid, that means halogens is zero oxidation state, but when it is present in halogen acid, now it will carry -1 charge. That means it has gained electron. So this electron that is gained by halogen, that is actually given by SO2. So that is why SO2 is reducing in nature. Then from HNO3 to NO2, because in HNO3 the oxidation state of nitrogen +5, but when it is converted to nitrogen dioxide, now it is +4 oxidation state. That means gain of electron. So we have the reactions here. Fe3 plus in presence of SO2 and water is also present. It is reduced to Fe2 plus. And what is the fate of sulfur dioxide itself? Now it is converted to sulfate ion. Now in sulfate ion oxidation state is +6, and when it is SO2, that is before reaction, here oxidation state will be +4 because we have 2 oxygen. So from +4 to +6 it has lost electron, so it means it is oxidized. And next reaction is halogen. Halogen is converted to X minus, that means it is actually halogen acid, but we have written it in dissociated form. H plus is also there, so if you take 2H plus from here, it will be HX, 2HX, and another 2HX that will be in SO2 2 minus. It is actually the we have written the equation here in dissociated form, so that is why it is like this. And if it is reacting with nitric acid, now nitric acid is converted to NO2 and SO2 itself is converted to sulfate ion. So one thing you can see, it is common in all the three equations, that in each case SO2 itself is converted to sulfate ion. Fine. It can also reduce potassium permanganate. Potassium permanganate is very strong oxidizing agent, and dichromate. Dichromate is also very strong oxidizing agent. And from in potassium permanganate, oxidation state of manganese +7, but after reduction with SO2, now the oxidation state is converted to 2 plus. That means from +7 to +2 it is also gain of electron. Similarly, K2Cr2O7, here Cr2O7 2 minus, and oxidation state is +6, but after conversion, that is after reduction, now it is Cr2SO4 whole 3. That means per chromium, 2 chromium atoms are there, and total negative charge 3 into -2, because per sulfate ion we have -2 charge, so total negative charge -6. So total positive charge will be +6, but 2 chromium, so that is why it is +3. So from +6 to +3, this is also gain of electron. So here SO2 is acting as oxidizing agent and itself is converted to sulfate. Okay, now this test, it is very, why it is important, because it can be used for identification test of SO2. So suppose you have SO2 and you that is want to prove that it is SO2. Suppose it is, if it is unknown sample, then how we can prove it? The presence of SO2, it can be proved with KMnO4. And whenever we choose any equation as any reaction as identification test, there must be some criteria present. And what are those criteria? There must be some visible change. I mean, it may be color change, it may be liberation of some gas, it may be precipitation formed. Anything is fine, but there must be some visible change. So here KMnO4, it has particular color, but when it is converted to +2, the color will be lost. So it proves that it is acting as oxidizing agent. And if it is K2Cr2O7, it is also having some particular color only when it is +6 state. But when it is in +3 state, now there is another color. So this type of color change is possible only when some reducing agent is present. So here we have this picture. So suppose we have some unknown solid and there is addition of HCl. Okay, so if there is a production of yellow precipitate and SO2 gas is generated, so this is SO2 gas. Now suppose you want to prove that this liberated gas that is liberating from the test tube, if it is SO2 or not, that can be proved if you are holding some filter paper which is weighted with potassium dichromate. Now potassium dichromate, it is having this type of yellow orange color, but in presence of SO2, now from +6 state it will be converted to +3 state, and when it is in +3 state, now there is a definite color change which is green. So this type of color change is occurring in presence of this gas. That means SO2 is acting as reducing agent here. Okay, and this unknown solid means it may be any sample, that is any sample on which when you are adding HCl there is liberation of SO2. So in this way, not just you are identifying SO2, you can also identify that what will be the unknown solid. So in the unknown solid there must be presence of sulfur. So in this way we can do this type of identification test in any reaction. If you are doubting that there may be liberation of SO2, you can do this test. Similarly, you can also take filter paper which is weighted with KMnO4 solution. So the purple color of KMnO4, that will be lost and the paper will be white. Okay. Next reaction with oxygen and with chlorine. Sulfur dioxide is oxidized to sulfur trioxide in presence of oxygen, and it is occurring at high temperature. So SO2, oxygen, and remember here we have some catalyst required which is vanadium pentoxide, and we are getting another oxide of sulfur which is SO3. Now this reaction is important because it is one of the important steps for the manufacture of sulfuric acid by contact process. Though we have not discussed yet how we can make H2SO4, that we are going to discuss after some time. There you will see that this step is very important step for production of sulfuric acid. It can also react with chlorine gas in presence of charcoal. So charcoal is the catalyst here, that is simply carbon, and it is giving sulfuryl chloride, SO2Cl2. So chlorine is acting as chlorinating agent here, and SO2 is converted to SO2Cl2. It also has oxidizing nature. Now SO2, it can show reducing nature, it can show oxidizing nature, both are possible. Now what is the reason behind it? Because sulfur is having +4 oxidation state when it is in SO2. Now from +4 it can have +6 state by losing electron, that is oxidation, or it is also possible that it is gaining some electron and it is reduced to another oxidation state, because for sulfur different types of oxidation state possible, right? It can, so that is the reason, as it is having oxidation state intermediate. Suppose if it is having oxidation state +6, then further oxidation not possible, because that is the maximum oxidation state of sulfur. But in case of SO2, as sulfur is having intermediate oxidation state, so it can switch to any of these species, S2- or +6. depending on what type of reagent you are using. So when it is showing oxidizing nature, now see the reaction. SO2 is reacting with another compound of sulfur, which is H2S. From +4, now it is converted to zero oxidation state. That means it is gain of electron. So here H2S is basically acting as reducing agent. Now you can also think that in H2S oxidation state of sulfur is -2 and it is losing electron and converted to H0. So with respect to sulfur which is present in H2S, with respect to that sulfur, obviously it is oxidation because H2S is acting as reducing agent here. But if you consider sulfur present in SO2, with respect to that sulfur, it is reduction because it has gained electron. Another example, SO2 reacting with carbon monoxide. Carbon monoxide is now oxidized to carbon dioxide and SO2 is reduced to sulfur. That means here SO2 is showing its oxidizing property. So that is why CO is converted from +2 state now to +4 state. So this is these two reactions are example of its oxidizing nature. Any doubt? It can also show bleaching action. Okay. When it is in presence of water, that is moisture must be present, it is able to decolor a substance. So that is the bleaching action. Now this is actually acting as reducing bleach. Remember there are two types of bleaching possible. One is reducing, another one is oxidizing. Now SO2, in case of SO2, the bleaching action that you are seeing, that is actually by reduction. And it is useful reducing bleach for papers, delicate materials such as clothes. So it has important application because of its bleaching property. So in presence of moisture, it is generating this nascent hydrogen, and this nascent hydrogen is actually responsible for bleaching action. Colored matter in presence of this nascent hydrogen, not oxygen. Colored matter in presence of this nascent hydrogen, now it is converted to colorless matter. And one very important information here is that this bleaching effect is not permanent. Unlike in case of chlorine also we have seen there is bleaching action. We will see it more in case of group 17 elements, that is halogen. So there you will see that in some cases bleaching action is permanent. That is, you cannot recover the color back. Once it is colorless, you cannot recover the color. But in this case, that is not the, that problem is not present. If you want to generate the color again, that is possible. So how it is possible? Oxygen in the atmosphere reoxidizes the reduced type, because here the bleaching action is because of reduction, it is not because of oxidation. So that is why as it is reduced, oxygen which is present in atmosphere, suppose you are keeping the colorless matter open atmosphere for long time, now this atmospheric oxygen, what it will do, it will oxidize again to the colored matter. That means reverse reaction now will take place in presence of oxygen, because the forward reaction that is actually happening in presence of nascent hydrogen, but in presence of oxygen now the reverse reaction is possible. So that is why you can regenerate the color. So remember, bleaching action of sulfur dioxide, it is not permanent. This is very important, that is feature of this bleaching action. Application of sulfur dioxide. It is used as food preservative, then bleaching agent to remove excess chlorine. So see, bleaching agent we have just discussed. Cold storage plant, it acts as refrigerant. Okay, so as that is, it is normally in gaseous state, right? So when it is very low temperature, it will have, that is when it is in a liquid state, obviously there is very low temperature. So in that case, it can act as refrigerant. It is used as reagent and solvent in the laboratory in manufacture of sulfuric acid by contact process. Remember, contact process, that step that we are mentioning here is the step where SO2 is oxidized to SO3 in presence of O2. So this is one of the important step of sulfuric acid. So SO2 is, we are using SO2 to produce sulfuric acid. This is application. For refining and decolorizing sugar as disinfectant and fumigant, liquid SO2 has been used in purifying petroleum products. So these are some of the applications of this gas. Next, we have a question related to this gas. Which of the following product is formed by the reaction of sulfur dioxide with chlorine in presence of sunlight? So it is the reaction SO2 plus chlorine. And remember, we have just discussed 2 slides before SO2, how it is reacting with chlorine and what product it is actually producing. Here you can see different types of sulfur oxygen chlorine products are there. Okay, but the product that is formed is SO2Cl2. So this will be the correct answer. Next problem, compound A and compound B both are treated with dilute H2SO4 separately. Remember, it is not mixed, separately. A plus H2SO4, B plus H2SO4. Gaseous liberated Y when it is A, and when B is treated with H2SO4, then Z is liberated. Both are liberated gas. Now, the liberated gas Y, it can turn acidified K2Cr2O7 paper green. Remember what we have seen in the identification test of SO2? And Z, which is the liberated gas in case of B, it can turn lead acetate paper, that is PbOSe2, to black color. You have to find out the compounds A and B. Here we have options Na2SO3, Na2S. So in both cases sulfur is present. Second option, you do not have any sulfur for A. Actually this is for A, this is for B. The first one is A, second one is B. So in 4 options, there are actually how many A, that is compound possibilities are there? Na2SO3, sodium chloride and sodium sulfite. And as B also, you have how many compounds? Na2S, Na2CO3, Na2H2O3, sodium thiosulfate and Na2SO4. 4 different options are there. Okay. Now one thing we are sure that, as we have just seen, that identification test of SO2, it can turn K2Cr2O7 paper green, from yellow orange color to green color, and that is possible because of the conversion of chromium +6 state to +3 state, and this can be done by SO2. That means from A we are getting sulfur dioxide gas. Now as we are getting sulfur dioxide gas in presence of dilute H2SO4, this option cannot be correct, NaCl, because NaCl there is no sulfur, right? And then Z turns lead acetate paper black. Now lead acetate paper, it is converted to black color. That means you are getting metallic lead. So from Pb2 plus, now you are getting metallic lead, and that is possible if there is some reducing agent present, from Pb2 plus state to Pb. So it is obviously gain of electron. So the gas Z, it must have some reducing agent, right? So we will see the reactions. Na2CO3 in presence of H2SO4, it produces sulfur dioxide. So this is actually Y. And these are the other products. But this type of reaction is not possible with Na2S. And NaCl, obviously it is not correct. You can easily cancel it out. So Na2S will be correct. Corrected A compound. Now Na2S is present both in option 1 and in option 4. That means B will be either sodium sulfite or sodium sulfate. Okay. Now first we will see what is the reaction Y when it is reacting with orange colored K2Cr2O7 paper in presence of H2SO4, because it is acidified paper. It is converted to chromium +3, green color. And this is the that is, just read this statement: Y turns acidified K2Cr2O7 paper green. So this is Y. Now what about Z? Now Z is generated from Na2S. Z is actually H2S. Now this type of reduction, that is lead acetate, this is lead acetate. Now it is converted to lead, sorry, I have said here it is Pb, it is not Pb, it is conversion to PbS. It is not metallic lead, it is lead sulfide. Okay, so H2S, it is in presence of sulfide ion. Pb, it is attached to acetate ion, but now it is attached to sulfate ion and acetic acid is removed. Now this PbS is actually this black color, that is responsible for this black color. So the liberation, actually this test, that is lead acetate paper is turning to black color. This is the identification test for H2S. Okay, that means in the second case Z is H2S and it can be generated only from Na2S, because see, when it is Na2S, it is -2 and this is +6. Okay, now if it is already Na2SO4, this reaction is not possible with H2SO4. But if it is Na2S, then this reaction is only possible. That is only in presence of Na2S. What is happening here? These two sodium ion now in presence of proton, which is coming from H2SO4, it is 2 sodium atom replaced by 2 hydrogen. But this type of reaction is not possible with other two sulfur compound, Na2S2O3 and Na2SO4. And Na2CO3, obviously this is not correct. We have already cancelled it because NaCl is also not. So correct option will be A is Na2SO3, that is either option 1 or 4, but B is Na2S. That means correct option will be this one. Okay, so this problem, is there any doubt? Should I discuss it once more? This is A, this is B. Any doubt? Oxoacids of sulfur. Remember, we have seen in case of group 15 elements, phosphorus, some oxoacids. In case of group 16 elements, in only for sulfur, now we will see some oxoacid. But before going to the discussion, just try to remember what is oxoacid. There must be presence of some, that is the central atom. If it is EOH must be present. Okay, so this type of bonding must be present in oxoacid, and there is also in some cases presence of E double bond O. So this E is here sulfur. Okay, it has huge number of oxoacid. And remember, some of these acid, though we are saying acid, but some of these acid do not exist as free acid. That means this H will be replaced by some metal. So that is why it is not free acid. They will be called as anion or salt. So if there is some metal atom present, it will be called salt. And if simply the H is missing, it will carry some negative charge. So in that case, it will be called anion. Okay. So one by one, we will see all the oxoacids. H2SO3, here oxidation state is +4. Okay, because if you just remove this 2H plus, it will be SO3. 2 minus 3 oxygen atom means total negative charge -6, so it must be +4 because 2 negative charge extra. This is known as sulfurous acid, not sulfuric. Sulfuric acid is H2SO4, but this is H2SO3. In this case, important properties, free acid doesn't exist. Okay, and it is strong reducing agent because here oxidation state of sulfur is +4. So it can donate electron and it will be now after reduction, it will be converted to +6 state. Okay, so that is why reduction possible. But this type of behavior is not possible if oxidation state is +6. This is the structure. Sulfur is attached with 2OH. Remember the general formula that I have said like this. So here we have double bond O and 2OH. At least one OH must be present. And here we have 2OH. Next is H2SO4. Now oxidation state is +4. sorry, +6, and it is also called oil of vitriol. Now this acid is stable, that all of us know. H2SO4, very common, and it can act as dehydrating agent. When it is in concentrated state, it can absorb moisture. That means dehydrating agent. And this is the structure. Now see, one double bond oxygen is extra. Just try to understand the difference with the previous one. This oxygen is extra. Next is H2H2O3, thiosulfuric acid. We have already seen sodium thiazole. Okay. Now see, just remove these two Na with H. Then it will be this acid H2H2O3. Here also free acid does not exist, and most of the time it remains as in some salt form. So this is the salt form because you do not have the H, rather you have metal, and all this compound is stable reducing agent. Thiosulfuric acid. Now the word, this term thio, it means that that is just replace this oxygen with sulfur. Then you will have this type of structure. Okay. And here oxidation state of sulfur, it is not that is only one type of oxidation state. Two types of oxidation state is there. So be very careful. Suppose this compound is given, and if it is asked what is oxidation state, and if you are following the method that normally we do, suppose you are thinking it is X, and for 2 hydrogen it is +2, for 2 sulfur it is 2X, and for 3 oxygen it is 3 into -2, that means -6. Overall molecule is neutral. So from this calculation, what you will get? You will get 6 minus 2, that is 4 by 2 plus 2. But this calculation is not giving you correct result. It is possible only when there is similar type of sulfur atoms present. But if you look carefully, these two sulfur atoms, their environment is not same. Okay, so that is why this calculation will not give you correct result. You have to know what is the structure. Then only you will be able to understand what is the oxidation state. In the first two cases, there is actually one type of sulfur. So by applying this method that we normally do, you can easily get the oxidation state. But we cannot apply it here. Two types of sulfur present. So the sulfur that is in the central sulfur, it will be having +6 state, and for this one it is -2. Okay, so two types of oxidation state. One is -2, another one is +6. Next molecule is dithionous acid. Oxidation state is +3. Now both the sulfur, as you can see, there is sulfur-sulfur bond, and these two sulfurs are in identical environment. So that is why only one oxidation state, which is +3. Now this molecule is significant because first, see, if you compare with the first two, that is H2SO3, H2SO4, there is no presence of sulfur-sulfur bond. But in case of these last two, 1, 2, 3, 4. For 3 and 4, you have sulfur-sulfur bond. Here we have double bond, here we have single bond. Number 5. Now see, this is the structure H2H2O6. Just compare with the previous structure H2H2O4. Now you have 2 oxygen extra, that means O6, and 2 oxygen extra means 2 double bonded oxygen extra for each cell. Dithionic acid +5. That is why ec. The previous one, it is ending with as, dithionous acid, but it is +5 because high oxidation state. Free acid moderately stable, but its salts are quite stable. Then oleum. So gradually oxidation states are increasing, right? Now it is +6. Oleum is disulfuric acid, or you can call it also pyrosulfuric acid. And this, why we are calling it disulfuric acid, because if you take 2 sulfuric acid molecule and just remove 1 water molecule, then you will get this type of structure. I'm trying to say this is H2SO4, right? Now, if you are removing 1 water molecule, then you will get this structure, And this molecule is having only this type of SOS linkage. No SS bond, SOS bond is present. This is strong oxidizing agent. And next one, H2SO5, this is also +6. This is paroxomonosulfuric acid. And when it is in salt form, it will be persulfate. Now, as paroxo is mentioned, that means OO bond is present. See? So that is why it is paroxo. Powerful oxidizing agent. And the reason behind it is that as it has paroxo linkage, so obviously it will be powerful oxidizing agent. Stable crystalline solid, that is this Carros acid. And remember why this is different from the other oxoacid, because it is carrying paroxyl OO linkage. And the next one, this is 5, 6, 7, 8. H2H2O8. Now this is also carrying paroxyl linkage, and it is also, because of that fact, it is also strong oxidizing agent. Okay, it is known as Marshall acid. And see here the difference is, just if you take another of this molecule and if you remove this H, and from the other molecule if you remove this OOH, then you will get this type of structure. So here we have again paroxo linkage, H2H2O8. It is also strong oxidizing agent because paroxo linkage is present. So is there any doubt in any of these oxoacid structure of sulfur? Next. So we have problem here which is related to this oxoacid of sulfur. So here some anions are given. That is, just remove the hydrogen of the oxoacid, you will get the anion. H2O4 2 minus means it will be H2H2O4, H2H2O5. In this way, we can get the corresponding oxoacid. The question is, you have to find that molecule where SS bond is not present. So in the oxoacid structures, we have seen in some cases SS bond is present, in some cases SS bond is not present. Okay, we have to find in which case SS bond is not present. So only one option will be correct. So these are the structures. This is H2O4 2 minus. The next one is H2O5 2 minus. SS bond present. This is also having SS bond. But C is H2O3 2 minus, and you do not have any, SS double bond is present, but still it is SS double bond. Only in the last case, which is H2O7 2 minus, here you have SOS bond, but no SS. So that is the reason it will be the correct H2O7 2 minus. Next question, which of the following oxoacid of sulfur there is OO linkage present? Okay, so some important information that you have to remember, that some oxoacid there is SS bond, some oxoacid there is OO bond, some oxoacid there is SOS bond, and in some cases there is also SOOS. Okay, so these are the some of the important features. H2H2O7, pyrosulfuric acid. Now this is actually this structure, H272 minus, that you have already seen in the last case. In this case, we do not have any OO linkage, as you can see from this structure. But we have to find which of these following there will be O. So this is not correct. Then sulfurous acid. Remember the first acid that we have seen, H2SO3. Here also we do not have any SS linkage. This is number 2 option. Number 3, H2SO4. So H2SO4 is only one oxygen now extra. So here also we do not have any. OO linkage, and the last one obviously it will be the correct because these two are not correct. So H2O8 peroxodisulfuric acid. Just see here, luckily these names are given in the question. So just even if you do not know the detailed structure, just focus on this part. It is containing the term peroxo. That means OO linkage will be present here. Okay, this is the Marshall acid. Remember the last structure that you have seen. Double bond O. Total number of oxygen is 8. H. So just from the term you can easily choose that this option will be correct. But suppose if there is no mention of name, then you have to draw the structure. Otherwise, if the question is given in this way, then just look at this name and choose the correct option. You don't have to write the full structure. Okay, any doubt? Next we'll see important compound of sulfur, H2SO4. So H2SO4, this is also one of the oxoacid of sulfur. Structure we have already seen. And this acid is colorless, odorless liquid. It is known as oil of vitriol, and it has wide application because it reacts with so many different types of compounds. So that is the reason it is called king of chemicals. Soluble in water, and when it is in contact with water, it releases heat. Now that is the reason if we want to prepare dilute H2SO4 solution starting from concentrated H2SO4 solution, the mode of addition should be you should add concentrated acid slowly, that is dropwise, to water medium. And remember with constant stirring because heat will be generated. So where the drop is actually falling, suppose this is water and the drop is here, so heat will be generated. But if you are stirring it continuously, then heat will be equally distributed. So if heat is just it is present at one particular position, then there is a chance of accident. So that is why we have to continuously stir the solution. So this is the correct way to make dilute solution. But if you are doing the reverse addition, that is you have taken H2SO4 and you are now adding water. So water you are adding in less quantity, already H2SO4 is present in large quantity. So this is not the correct way because explosion will be there, because a large amount of heat will be generated. It will even char wood and most other organic matter when it comes in contact with this. It is corrosive in nature to metals and also tissues. So we shouldn't touch it with bare hands. Now there are two important methods for the commercial preparation of H2SO4. One is lead chamber process, another one is contact process. Remember contact process, this term we have already heard in sulfur dioxide. One of the important steps, SO2 plus O2 producing SO3. Lead chamber process. First step is the mixture containing sulfur dioxide, air, that means it is nothing but presence of oxygen, nitric oxide, that means NO. So you have taken SO2, O2, NO, and you are treating it with steam. That means water. So first there will be formation of sulfuric acid. So in stage 1, NO is basically the catalyst. First it is oxidizing, that is it is oxidized in presence of oxygen and it is oxidized to NO. In the second stage, now sulfur dioxide is reacting with this NO2 which is formed in the first step, and it is now producing SO3 and NO2. See here catalyst is regenerated because that is the feature of catalyst, right? And this SO3 finally reacting with water and it is forming H2SO4. So these are the three important steps. So our starting materials are SO2, air, and catalyst, which is NO. First step, catalyst is oxidized to NO2. Then this oxidized catalyst is oxidizing SO2 to SO3. This is also oxidation, and itself is reduced to its original form, which is NO. And in the third step, the sulfur trioxide reaction with water, and it is producing H2SO. So this is the lead chamber process. Okay, see here also we have used sulfur dioxide, not just in contact process, here also we have used it. The second method, that is contact process, step 1. So in step 1, first we will make sulfur dioxide. And how we are doing so? This is made by heating sulfur or sulfide ores. So here you can start the reaction either with directly taking sulfur, or you can also take some ore of sulfur. So here we have iron pyrites. In the first case we are getting SO2. In the second case also obviously we are getting SO2, because we are preparing SO2. So obviously SO2 will be produced, and here the fate of iron is, it is converted to oxide. So look at this picture, sulfur and dry air. Dry air is nothing but oxygen. Now sulfur in presence of oxygen, high heat, there is production of SO2. Now this SO2 in presence of 450 degrees centigrade and catalyst V2O5, the next step will occur. So let's see what is the next step. The next step is formation of SO3. SO2 is oxidized with atmospheric oxygen. So see, SO2 is again reacting with oxygen in this portion in presence of catalyst V2O5, vanadium pentoxide. Here temperature you have to maintain in this range, and pressure is 1 to 2 atmosphere. So the reaction is SO2 is converted to SO3. This is just a catalyst, and this is exothermic reaction. Look at the value, minus 196.6 kilojoule per mole. And third step, it is the same as you have seen in case of, almost same, not exactly same, in case of lead chamber. In lead chamber, the last step is SO3 is reacting with water, it is forming H2SO4. But here what we are doing, first we are converting SO3 in presence of H2SO4. So we are making H2SO4, that is fine, but we are also taking the help of H2SO4, 98%. Here first SO3 is broken up in 98% sulfuric acid to give pyrosulfuric acid, which is nothing but oleum. Remember, this is also one of the oxoacids that we have already discussed in the table of oxoacids. Now this oleum is diluted or weakened with water. So directly SO3 is not treated with water. First it is converted to oleum, and then oleum is reacting with H2O, and it is producing 2 H2SO4, because here we have 2 sulfur. Okay, so these are the 3 steps of contact process. And remember, the second step is exothermic. It is reversible also. So the forward reaction here leads to decrease in volume. Now why it is decrease in volume? See, just look at the second step. It is that is, in the starting material we have taken SO2, which is gaseous. This is also gaseous, and product is also gaseous. Now see here, 2 moles, 1 mole. So from 3 moles you are getting 2 moles. That means there is reduction in volume. Volume is decreased. So in the second step, volume is decreased. That means according to Le-Chatelier principle, if you are increasing pressure, the system will try to move towards that direction where volume is less. Because according to Le-Chatelier principle, if a system is already in equilibrium and you are changing some conditions, that is, you are creating some disturbance, it may be pressure, volume, concentration, anything. So the system will try to cope up with this situation in such a way so that the disturbance effect is as minimum as possible. So as we are increasing the pressure, the system will move towards forward direction, because in the forward direction volume is less. Okay, so the increase in pressure that we are doing from outside, that effect will be minimized. So that is why, as it is decreased in volume, pressure must be maintained 1 to 2 atmosphere. If it is less than that, reaction will not be possible. And remember, it is exothermic also. So that is why low temperature should be maintained. But see, we are saying low temperature, but here it is 400 to 450. Why it is so? One thing you have to understand, that though it is exothermic, and we know that when energy is released, exothermic means what? Energy is released. So according to again Le-Chatelier principle, if you are increasing temperature, the system will move towards that side where heat is absorbed. That means the system should now move towards backward direction, towards the starting material. But that is obviously not desired. But still we are applying high temperature. What it is so? It is because you have to provide the required activation energy. So though we are saying that it is exothermic, but to overcome the activation energy, we have to provide this temperature. So that is why in bracket it is mentioned, it is low, but should not be very low. Okay, and this high, low, all these terms are actually relative. If I am saying that temperature is low or temperature is high, there is no meaning in that. You have to compare with some other value, then only it is high or low, right? So here we are saying low, but don't think that it is very low temperature, like less than 100 or something like that. So to overcome the activation energy, we have to provide this much of heat, and once that reaction is started, then further temperature, if we do not maintain, then also it is okay, because it is exothermic reaction. So low temperature, high pressure are the favorable conditions for maximum yield, and it is based on Le-Chatelier principle. Okay, any doubt in this process? Should I repeat any part? Physical properties of this acid: colorless, dense, oily liquid, specific gravity is high. If you compare with water, you'll be able to understand. So that is why if you see concentrated H2SO4, you will see it is very viscous type of nature, very dense, not like its fluidity is very high. Okay, that is compared to water, fluidity is less because high specific gravity. Melting point, boiling point in Kelvin unit given. The high boiling point, 611 Kelvin means, if you convert it to degree centigrade, 300 something will be the value. So it is quite high boiling point. And thick nature, it is because of hydrogen bonding. Hydrogen bonding is present in H2. So that is why boiling point is high, because you have to break those hydrogen bonds. Concentrated sulfuric acid, it has tendency to absorb water. So it has strong water affinity. And this property is utilized in some chemical reaction. So suppose in some chemical reaction, you need to remove water from the medium, then this can be used, provided it is not creating any other side reaction. A lot of heat is generated when the acid is mixed with water. So as I have already said, how it should be added, that is whether you will add H2SO4 to large amount of water, or you will add water to large amount of H2SO4. No, the second one is not correct. The first one is correct method. Acid is diluted by adding it to water gradually, remember, with constant stirring, so that the heat is distributed properly. So here important notice: never add water to sulfuric acid. Now chemical properties. Here we have 4 categories in which we have divided the chemical reactions of sulfuric acid. It is known as king of chemicals. That means it can react with so many different types of compounds. Okay, so in some reaction you will find this acidic character. In some reaction you will see that it is absorbing water, because it has water absorbing property. In some reaction its low volatility will be utilized, and in some reaction you will see it is acting as oxidizing agent. So questions like these are very common, like suppose some reactions will be given and it will be asked that in which of this reaction you can see that it is showing oxidizing property. So this type of question is very common. Or in which reaction it is showing strong affinity for water, like this type of question. Okay. So first we will see its acidic character. It is strong diabasic acid because 2H plus you can get when it will be dissociated. It ionizes in 2 stages. In step 1, in presence of water, H plus is associated with H2 and you are getting hydronium ion, and this is the HSO4 minus. Now still there is one more hydrogen, so further dissociation is possible. So in second step, the dissociation is now HSO4 minus. It is again giving another H plus, you are again getting hydronium ion, and now it is sulfate. Now look at the dissociation constant values. The first case it is very large, greater than 10. But in the second case, it is comparatively less, 1.2 10 to the power minus 2. That means 0.012. Obviously, compared to 10, it is very, very low. Okay. So in this way, it is acting as strong diabasic acid. So based on its acidic character, let's see some reaction. Sulfuric acid forms 2 types of salt. Obviously, it will do so because 2 replaceable hydrogens are there. So when it is forming compounds by the removal of the first hydrogen, then the compounds will be called bisulfate, because now this type of anion you will get, and bi this term is used because of this hydrogen. Or you can also call it acid sulfate or hydrogen sulfate or normal salt. All these are same thing. Now see the reaction H2SO4 first reacting with NaOH, and it is forming NaHSO4. That means only one hydrogen is replaced by Na. Still you have one more hydrogen. So this is called sodium hydrogen sulfate or sodium bisulfate. You cannot call it sodium sulfate. Sodium sulfate is the second one, when another H is also removed. So if it is that both the hydrogens are replaced by sodium, now this salt will be called as sodium sulfate. Okay. Sorry, it is what I have said in the first point. When it is HSO4 minus, that is for the first equation. Suppose this is the first equation. Then you can call it bisulfate, hydrogen sulfate, or acid sulfate. So it will be ended here. So and sulfate will be called if it is equation number 2. So this is for equation number 1, this is for equation 2. So normal salt is basically this one, that is the second one. Okay. So if one hydrogen replaced, it will be called bisulfate, hydrogen sulfate, or acid sulfate. Acid sulfate because still you have one more acidic hydrogen left. So that is why it is called acid sulfate. And the second type of salt, that is why it is normal salt, because both the hydrogens are. Low volatility property, how we can utilize it? Low volatile, that is, it is not easily, it will be evaporated. Low volatile. Because of its low volatility, it can be used to manufacture more volatile acid. So to prepare some other volatile acid from their corresponding salt. That means if you are preparing HCl, suppose you are preparing HCl, so obviously you have to take some salt where chloride is present. Okay. And how we can do so? See this reaction. Concentrated sulfuric acid, it can liberate HCl from NaCl. So corresponding salt here we have taken sodium chloride, which is the source of chloride ion, and in presence of sulfuric acid you will get HCl. Now here we have general equation. We have taken Mx. Now X may be F, it may be Cl, or it may be NO3. So if it is F, you will get HF. If it is Cl, you will get HCl. If it is NO3, you will get nitric acid, HNO3. So all these acids you can prepare, but you have to take the corresponding salts. If you want to make HF, obviously you have to take fluoride salt. If you are preparing nitric acid, you have to take nitrate salt. Okay. And what is the fate of H2SO4? Now this metal, that is whether it is sodium, potassium, whatever it is, now it is present with sulfur. Another example, now it is CaF2. Okay. So CaF2, that is we have now taken group 2 metals. So that is why the formula is different. CF2, it is not MX. MX is possible only when it is NaCl or KCl like this. And it is producing the more volatile acid, that is compared to H2SO4 more volatile. And the fate of H2SO4, it is now calcium sulfate. So in this reaction, we can see its that low volatility property is utilized. Dehydrating property. As the acid is intense dehydrating agent, that means water absorbing property, it will be utilized as a part of drying many wet gases. So you can dry some wet gases, provided one condition must be there, that they do not react with the acid. Otherwise, whole purpose will not be successful. Our purpose is just to remove water. It is not that we want H2SO4 to react with that compound, that is gas. So that is why it must be, you have to make sure that it is not reacting with the acid, then only you can use it to dry the gases. Here we have some other examples. Formic acid in presence of H2SO4, if water molecule is removed, that means H, which if it is removed, you will be left with CO. Then glucose in presence of H2SO4, it is completely charred, it is converted to carbon. So carbon is completely removed, 6C, and 6 water molecules are there. So all these are basically organic compounds, right? Formic acid, glucose, ethanol. So these three examples, you can see organic compound. Ethanol in presence of H2SO4, now it is converted to C2H4. C2H4 means ethylene. This is C2H4. If you remove water from ethanol. And crystal, that is in crystal, when there is water molecules present, that is water molecules of crystallization, those acids, those water molecules can also be removed. So it is CuSO4 containing 5 water molecules, but in case of H2SO4, now you are getting anhydrous CuSO4 because all the water molecules are removed. Okay. So is there any doubt? We have seen here the 3 properties: acidic property, low volatility property, dehydrating property. One more is left, which is very important, and that is oxidizing power. In some reactions, we can see it's oxidizing. So in these 3 types of reaction, is there any doubt? So here we have oxidizing property, but it will take some time, so better we will discuss it in the next class. So this property that is among 4 properties, 3 we have discussed and 1 property we will do it in the next class. Okay. So regarding all the slides in the whole class, is there any doubt? Okay, so we will end the session here. Thank you for listening.